Hey, welcome back. So we're going to finally dive into Chapter 5. Due to some of the limitations in time, I will be going through sections 5.1 through 5.3 in a sort of mixed way throughout this video and the next. In today's video, we will just be focusing on the big ideas, and I hope the next video will help bring the whole picture together. So let's dive straight into a problem and see how we would solve it. You're riding a bicycle starting at some place S, and you're riding it to the right on the number line. And you're going 15 feet per second. So the question we want to answer is, how far have you gone after 8 seconds? I'm sure we've all done a problem like this stuck in traffic, but let's just do it together really quickly just to make sure we know the basics. We're going 15 feet per second and we're traveling for 8 seconds, so we've gone a total of 15 times 8 or 120 feet. But the question we should all be asking ourselves is there another way to interpret this 120 feet? Let's start by looking at the graph representing our velocity. Since at all time we're going 15 feet per second, our velocity is just a constant function, so our graph is just a horizontal line. But where can we find that 120 feet? Notice that if we fill in all the area below our horizontal line, between time 0 and times 8, we get a rectangle. Its height is 15 feet per second because the velocity is the dependent variable and its units are feet per second. The base is represented by the independent variable, which in this case is time, whose units are seconds. So the total area of this rectangle is base times height, so 8 seconds times 15 feet per second, which gives us 120 feet. So in some sense, the area under our velocity function represents the total distance we traveled in this problem. Back when you learned the product rule, some of you may have been shown the idea that anytime you have the product of two quantities, there is often a way to interpret the problem using areas. This is yet another example of this. So now let's look at a slightly trickier version of the same problem. In this problem, we will start riding our bicycle from a standstill, and our velocity is going to increase 1 foot per second every second. So we're going to ask the same question. After 8 seconds have passed, how far have we gone? So if we're going to use the same logic as we just discovered in the previous example, we should interpret this as the area under some graph. Specifically, we want the area under the graph of the velocity function, so we need to figure out what that looks like. So if our velocity is increasing 1 foot per second every second, we know that after 1 second, our velocity is 1 foot per second. After 2 seconds, it's 2 feet per second. After 3 seconds, it's 3 feet per second, and so on. That means our velocity at any moment is just equal to the amount of time we've spent traveling. This function can be represented by the function v of t equals t. I've included the graph here. So all we need to do is find the area under this graph above the t-axis. Also, I should warn you, this graph is not to scale because computer screens aren't perfect squares, so it skews the scaling a little bit. So pause the video here a minute and see if you can figure out how far we've gone. Luckily, we're left with a triangle whose area we know. The area of the triangle is just 1/2 the base times the height. The base is still 8 seconds. The height in this case is now 8 feet per second, so the total area under this graph must be 32 feet. It's okay if you're still skeptical about whether the area we just computed is actually the total distance traveled. I'm going to ask you to trust me for now, and I'll try to convince you about this again in a couple slides. Now let's raise the bar a little. Like the previous problem, you'll be gaining speed at 1 foot per second every second. Now let's add that you were going 7 feet per second at the beginning. Try to figure out your total distance traveled over those 8 seconds. To help you, I've included a graph of the velocity. So pause the video now and see if you can figure this one out. So the key to doing this problem is realizing the area we're trying to compute is really the sum of the area of a rectangle and triangle. Using a combination of the previous two problems, we can compute the area by computing the area of each independently and then adding up our answer. So as always, let's make things even more complicated. Let's say now that our velocity is given by the function v of t equals 9 minus t squared. We know that this will be equal to 0 when t equals 3, so between time 0 and time 3, how far did we go? Sticking to our previous interpretation, it must be the same as the area represented by the blue shading here, which is the area below the function v of t equals 9 minus t squared. Unfortunately, this isn't a rectangle, triangle, or some other polygon whose area we already know, which means we're going to have to figure out how to compute it some other way. So we want to reduce this problem into computing an area that we already understand how to compute. There are many ways to do it, but for now we're going to just try to approximate the area by splitting up the domain and making rectangles that are roughly the size of the area we're looking for. You might want to ask, why rectangles? Why not some other shape? Well, in fact, you can use other shapes. For example, trapezoids can be pretty effective at doing what we're doing, but the area of a rectangle is just easier to compute. I will point out, if what you're doing is programming a computer to estimate areas like this, since computers don't mind arithmetic nearly as much as we do, using a rectangle is actually a bit clumsy. On this slide, you'll see the graph of our function with 3 rectangles overlaid, which I made as follows. First, I split the interval 0 to 3 into 3 intervals of length 1. Above each of those intervals, I have drawn a rectangle whose height is equal to the value of the function on the left side of each interval. So let's quickly compute the area of these 3 rectangles. The first one has height 9 and base 1, so it has area 9. The second one has height 8 and base 1, so it has area 8. The last one has height 5, still base 1, so it has area 5. So altogether, these 3 rectangles comprise an area of 22. If you look at the shading, you'll realize that these rectangles are actually covering more area than simply the area under the function. So the 22 is an overestimate for the area under our function. So did we have to pick the height of our rectangles to be equal to the value on the far left of our interval? The answer is no. There are a lot of ways you can go about choosing what height of each rectangle you want. It should be in some way tied to your function, or else you're not really using any information. You sometimes use the left or right side of your interval because it's easiest to compute what values you're going to plug into your function. Sometimes it's useful to use the absolute max or absolute min of your function on each subinterval, because then you'll know for sure whether your estimate's high or low. For example, in this graph, we drew the rectangles using the value of the function on the right side of each interval. Notice that the third rectangle has height 0 because the function is 0 on the right, so it's contributing 0 area. Additionally, the estimate we would get using these rectangles would be lower than the actual area. The fact that the first estimate was higher and the second one was lower is due to the fact that our function is decreasing. But if our function was changing from increasing to decreasing throughout the interval, we would really not have an idea of whether our estimate was high or low, well, in general. So for the rest of the video, we're going to use the value of the function on the left side of each subinterval for our height. Again, this is a choice we're making for the sake of this video, but it's important for you to keep track of that. So we know our approximation isn't that great. We're definitely overestimating the actual area. So the next question we can ask is, how can we get a better estimate for the area? Well, as you can see, part of the problem is the function changes a lot on each subinterval, but the height we're using for each rectangle doesn't account for that. So let's see what happens if instead of 3 rectangles, we use 6 rectangles. Notice with 6 rectangles now, we're actually getting a better estimate. The error we removed is represented by the light blue rectangles you see here. So this means if we use even more rectangles, our estimate should get even better. Here's what it looks like with 12 rectangles. And this is what it looks like with 24. Each time you see, our estimate is getting better and better and better. I've included the area of the rectangles on each of these pictures. As a spoiler, I'll tell you that the area under our function is actually 18. So as we get more rectangles, we notice that our approximate area is getting closer and closer to 18. By the end of this video, we will actually compute that area. So you may be noticing we're going to need to add the area of a lot of rectangles. For this reason, let's take a quick detour and remember some notation we've seen before. That is summation notation. I'm going to go through this quite quickly, partially because we've seen it before, but also because there's new material we need to focus on in these videos and for the rest of the semester. This notation gives us a shorthand way to write very large sums. It is particularly useful when the terms follow a nice pattern that can be described as a function of k. So let me quickly point out the major features in this notation. First of all, there's a sub k, which tells you a general formula of the terms in the sum as a function of k. Under the sum sign, you see the term k equals m. K is the dummy variable that you will plug various values into when computing the sum. You will plug in for k every integer value from m all the way up to n. On the bottom left of the slide, you'll see 3 examples of this notation in action. In the first one, for example, a sub k is equal to k, and we're plugging in integer values from 1 all the way up to 5. On the bottom right of this slide, you'll see 4 common formulas. The first is for the sum of 1 with itself n times. The next 3 are the sum of the first n natural numbers, the sum of the first n natural numbers squared, and the sum of the cubes of the first n natural numbers. The right-hand side of each of these identities is known as the closed form of the sum, because it no longer uses the sum notation and just expresses the sum as a formula in terms of n. Since we're working with a quadratic in this example, we will be using the first and the third in this video. You should feel free to pause the video and look at this slide as long as you need to make sure you understand the notation. Here are 2 other major properties of summation notation. The first is the sum and difference rule, the next is the constant multiple rule. They look a lot like properties you've learned about derivatives and integrals thus far, but they're actually based on things we've learned in previous classes. The first one is really just the same as the commutativity of addition. The second is just a distributive property. Challenge yourself to see why this is true. It's okay if you still feel shaky with this notation, but I do recommend you review it. While we won't be using it too much in this class, a lot of Calculus 2 depends on this notation, as one of the major topics you will cover is the convergence of infinite sums, which you cannot write in any other way. So let's get back to the business of computing the area under our curve. As we are going to study the sum of more and more rectangles, we are going to need to use the sum notation we just discussed. Before that though, let's write down the area of just one rectangle. So in this picture, we have broken up the interval from 0 to 3 into 24 rectangles, each of which has width 1/8. That 1/8 comes from dividing the interval 0 to 3 by 24. For the height, we've used the value of the function at the left endpoint. Okay, so we have n rectangles and we're looking at the kth rectangle. Since our interval has length 3 and there are n rectangles, each one must have width 3 divided by n. Because this is the kth rectangle, the left endpoint is actually the k-1th endpoint. Since each rectangle has width 3 over n, that means the height on the left side must be v evaluated at 3 over n times k-1. Multiplying those together gives us the area of the rectangle. So what should be the total area of the rectangles? Well, it should just be the sum of the formula we just got there from k equals 1 to n, 1 for every rectangle. Since we know the more rectangles we use, the closer our estimate gets to the area under our velocity function should just be equal to the limit of the total area of the rectangles. So let's just this once go through and compute it this way. So given the total area of all the rectangles, let's start out by simplifying each term into a formula that we can manipulate more easily. We will do this by first plugging in the value into our velocity function, then manipulating the symbols until we have something that's easier to work with. Next, we'll plug in our simplified form into our sum, and then use the properties of sums to further simplify it. The trickiest part here is to remember that n, which is the total number of rectangles, is not a function of k, which is each individual rectangle. So both 1 over n and 1 over n squared act like constants and can be pulled out of the sum using the constant multiple rule. So finally we use the sum of a constant and the sum of consecutive squares to simplify this into what's called a closed form. Or in other words, a formula that no longer contains the sum notation. Both of these identities can be found on a previous slide. To finish up the computation, we now need to find the limit as the number of rectangles, or n, goes to infinity. Fortunately, this limit has a form that we've computed many times, so we take the limit and find that the area must be 18. Thus, we have found that the limit of the sum is actually 18, which is the area under our velocity function. So the answer to our original question is that we've traveled a total of 18 feet from our original starting point s. We just computed the integral from 0 to 3 of 9 minus t squared with respect to t, which symbolically is written as you see on this slide. The notation is very similar to that of the antiderivative, and that's no accident, as we will see in section 5.4. As a quick warning, the definite integral only represents the area between the graph of a function and the x-axis when the graph is not negative. In the next video, we will see that the definite integral of a negative function will be equal to the negative of the area its graph bounds with the x-axis. This has to do with the fact that a negative velocity implies that you're moving to the left on the real line rather than the right. So, in summary, we have shown that the definite integral from 0 to 3 of 9 minus t squared dt is equal to 18, which you can write as seen here on this slide. So here are 3 things I would like you to take away from this video. First of all, we saw that the area under the curve of a velocity function represents the total distance traveled if the velocity is positive. The second thing is, if you notice in all the questions I asked, I always said you started at some point s. First of all, this should show you that once you know your velocity, your total distance traveled, as long as you're always moving right, is independent of where you start. But it also should highlight the fact that without knowing where you start, you don't actually know where you are. So in many ways, the starting point s was playing the same role that the plus c was playing in sections 4.8. The last thing you need to know is that we don't always have to compute limits like we did in this video to find the definite integrals of functions. 5.4 will teach us a much quicker way to do it in general. So thanks again for sticking around for another video. I hope to see you all again soon.